Very much. I'm glad to have the chance to give this talk. It's part of a 40-page paper that 45 that I've cut down to about 30 slides, and it's a strange talk. So let's see, how do I do next slide? I guess I did this, Kate?
Yeah.
Okay, I did it. Okay, this is all very strange. I've been working with Lee Smolin, a physicist, Marina Cortez, a cosmologist, Andrew Little, her husband, who's a cosmologist, and I will be using input from Paul Davies, who I think you may know. And I'm stumbling across something very odd. The paper is submitted for publication. This is the first time I've talked about it. So I'm going to read the abstract so that you see the overall view. It's all going to be very strange. Substantial grounds now exist to doubt the universal validity of the Newtonian paradigm. I'll explain what I mean in a minute, more detail, but it requires a pre-stated and fixed phase space of all the possibilities. The second law is stated only in fixed phase spaces, so it's also in doubt. This is very strange. The universal validity of the Newtonian paradigm may stop at the onset of evolving life, biospheres. I will tell you that living cells and organisms are something that I will call Kantian wholes, and they achieve something absolutely amazing called constraint closure, and they do thermodynamic work to construct themselves. So cells literally build themselves. Automobiles don't build themselves. Our cells build themselves. Evolution constructs an ever-expanding phase space. This is quite stunning, and it seems to be true. So we can ask something we can't ask in standard statistical mechanics. The phase space of statistical mechanics is fixed. It's the fixed liter box of gas. If the biosphere is constructing an expanding phase space, we can ask, what is the free energy cost per added degree of freedom? Because it's building its phase space. The cost is presumably roughly linear or sublinear in the mass of the thing that's constructed. But the stunning thing is that the resulting expansion of the phase space is exponential. A testable implication of this, the fourth law, which is that it gets cheaper and cheaper to add the next degree of freedom because the cost is linear and the expansion is exponential, is that at constant energy input, the biosphere can construct itself into an ever more localized subregion of its expanding phase space. This is confirmed. The localization of our biosphere in its protein phase space is at least 10 to the minus 2,540. The localization of our biosphere with respect to the molecules of organic chemistry, CHNOPS, comprised up to 350,000 atoms, is extremely high. It appears that entropy in the evolving biosphere has decreased. If so, the universality of the second law fails. If it fails, and we have taken an increase in entropy to be the arrow of time, that may fail too. So this is all more than strange, and the first time I've talked about it. See what you think. It's online and submitted for publication. So I have to read it because I have no equations and no visuals other than the slides. So the second law of thermodynamics is the most well-established theory of classical physics. So it tends to, entropy tends to increase, but must it be true? The conceptual foundations of the second law are two claims. The Newtonian paradigm, the system is in a pre-stated and fixed phase space, and the ergodic hypothesis, the system spends equal times and equal volumes of phase space. So both of these claims are central to all of classical and quantum physics. So it's very strange to doubt them. So you know this, but let me state it explicitly. Here's the Newtonian paradigm. State the relevant variables. For Newton, these are position and momentum. State the laws of motion and differential form that couple the relevant variables. For example, for Newton, there are his 3 laws of motion and universal gravitation. 3, define the boundary conditions of the system. Here's the crux part. The boundary conditions thereby define the pre-stated and fixed phase space of all possible combinations of the values of the relevant variables. So the phase space is that space in which things happen, of all the possibilities. State the initial conditions. Given the initial conditions, integrate the equations of motion to obtain a trajectory that's entailed from the differential equations of the system in its fixed phase space. For classical physics, this is a trajectory. In quantum physics, on most interpretations, it's an entailed trajectory of a probability distribution, then a debate about what we mean by measurement. So here's the ergodic hypothesis. The system spends equal time and equals the volumes of its fixed phase space. The ergodic hypothesis abandons integrating Newton's equations of motion in the box. So you all know this, so I won't repeat it. But the critical thing is that the second law says that this is really critical. The localization of the system in its fixed phase space tends to decrease. You start with all the particles in the lower left corner of the box, and they diffuse all over the box. So I want to say again, it's of fundamental importance that the second law depends upon the Newtonian paradigm of a fixed phase space. So I'm now going to take you into territory that's going to be utterly unfamiliar. So let's take our time. This is very new. Most of it is now published. Here's the issue. Does the universal validity of the Newtonian paradigm hold? So this is an enormous issue in physics and beyond physics. There's increasing ground for doubt. So I'm going to show you 4 grounds to doubt the universal validity of the Newtonian paradigm. Smolin points out that no mathematical object, such as a set of equations, can entail the evolution of the entire universe because entailing relations are timeless, but time and now are real. Smolin knows general relativity perfectly well. He was one of the co-inventors of loop quantum gravity. If we take, where obviously in general relativity, there is no now, and time doesn't flow, it's a dimension. But Lee knows all of that, and he's saying time is real. If so, a timeless mathematical object has a fixed phase space. If time and now are real, as Smolin has wished to say for a long time, there can be no fixed phase space. Therefore, the Newtonian paradigm cannot be universal. I want to stress Lee Smolin invented, one of the 2 inventors with Carlo Rovelli of loop quantum gravity. So he knows the issues. And he says, if we say that now and time are real, there can't be a fixed phase space. Second, this is quite stunning. Abigail Devereaux and colleagues, they pause and hear this, have shown that no modeler inside the universe can have a complete model of the universe. Basically, what she has shown mathematically is that no finite list of true-false propositions can exhaust the world. And that's how she shows that no modeler inside the universe can do it. It's not the same as the, I'll come back to it. So if this is true, it rules out a final theory that entails the evolution of the universe. So the Newtonian paradigm is not universal. By the way that Smolin brings this up is to point out that in physics, we always divide the universe into our system and within the boundary conditions, and then everything else. But for the whole universe, Smolin says, there is no everything else. And so we can't make the move of defining a fixed phase space. And that's lying behind point A. I'm going to tell you now about some work that I have done. It's very strange, okay, with my colleague Rolly. we have we have shown, this is now published, excuse me, excuse me, sorry. We have shown that it is not possible to use any mathematics based on set theory to deduce the ongoing evolution of ever new adaptations to the evolution of life. For example, life started around 3.5 billion years ago, and there were no kidneys and no eyes at the start of life, but kidneys have evolved and eyes have evolved, and we have shown that you cannot deduce that. That means that the evolving phase space includes these ever new adaptations. Thus, the evolving, ever-changing phase space cannot even be deduced. Therefore, there's no fixed phase space. The corollary, this will annoy you, is that there can be no final theory in a universe containing at least one evolving biosphere. If so, the universality of the Newtonian paradigm fails. So the clear implication of Kauffman and Rowley is that the phase space of evolving life is not fixed. The vast increase in the abundance and diversity of life in the past 3.7 billion years hints, but does not prove that the phase space of the evolving biosphere has increased, which will be something I come back to. The fourth grounds is very recent. This is work with Marina Cortez, Lee Smolin, Andrew Little, and myself. It's all online and submitted for publication. Maybe it's accepted for publication now, I'm not quite sure where, but it's quite striking. The fourth ground to doubt the universality of the Newtonian paradigm is Rees. General relativity and cosmology assume this paradigm as foundational. Cortez et al. Undertook the analysis of the complexity of a biosphere compared to the abiotic universe to assess the implication of the existence and life on the universe for the price of the initial state of the universe. The price for the initial state is the past hypothesis. Given the Newtonian paradigm with its fixed and unchanging phase space, the second law, in which disordered complexity increases, and the present complexity of the universe, then the initial state of the universe must have been correspondingly very low entropy. So the complexity of the abiotic universe is estimated to be this enormous number, e to the 10 to the 124th. If that's the complexity of the universe now, the entropy of the initial state was its reciprocal, 1 divided by e to the 10 to the 124th. And Penrose points out how difficult it is this price to be paid for the past hypothesis. So let's go over the structure of the issue here. We've assumed the Newtonian paradigm. We assume the second law where order decreases. So the complexity of the universe now, if we can measure it, is some number, and it's e to the 10 to the 124th on lots of estimates. Then the initial state of the universe for the past hypothesis, such that we have an arrow of time due to the second law, is the reciprocal. And basically, Penrose points out, how did God manage to get the dark that precisely to get to a state that's that Boltzmann suppressed? So here's the work of Cortez. It happens that I'm one of the authors, but I rely here on Cortez and Andrew Little mostly. So Marina and Andrew estimates the complexity of our single biosphere up to the first encoded protein synthesis about 3 billion years ago. It makes this price very much higher. It's not the reciprocal of e to the 10 to the 124th, but for single biosphere, it's the reciprocal of e to the 10 to the 237. Namely, the complexity of our biosphere is on the order of e to the 10 to the 237. So e to the 10 to the 237 is vastly larger than e to the 10 to the 124th. Please take this in. We're going to come and doubt it in a moment. But if this is true, the complexity, the number of degrees of freedom in the biosphere is vastly larger than the rest of the universe. It's very strange. So because this is vastly larger, so if we accept it for the moment, we have to conclude that the phase space of the biosphere has in fact expanded enormously. What I'm telling you is transformative if it's true, because you can't get it under the Newtonian hypothesis. And then the question will be, is it true? And for example, how did that happen? Which is one of my concerns. So here's the three choices for cosmology, given what I've told you. We could just deny the results of Cortes at all. It's just not true. Suppose that we accept Cortes's result, and we want to maintain the universality of the Newtonian paradigm and the second law. Fine. Then we preserve current cosmology, but in doing so, we also preserve a required price for the initial conditions, and we agree to pay this now vastly higher price. So if Penrose was worried about e to the 10 to the 124th, what's he going to say about e to the 10 to the 237th? It's beginning to be ridiculous to think that the universe started in a Boltzmann suppressed state that's 1 over e to the 10 to the 237th. But we can hold that view. But the price of the initial state is conditioned on the truth of the universality of the Newtonian paradigm and the second law. So our third choice is we can choose to abandon either or both of the universality of the Newtonian paradigm and the universality of the second law for the cosmological evolution of the universe. Please take this in. Here's this result, and the first thing you want to do is doubt it, throw it out, ask that it be repeated and all of that. For the purpose of this talk, let's accept Cortes's number. The complexity of the biosphere is vastly greater than the complexity that we know of for the entire remaining universe. If it's true, how did that come to be becomes an enormous question. And so those are our choices. Since the second law depends upon the Newtonian paradigm of a pre-stated and fixed phase space up, giving up the universality of the Newtonian paradigm calls the second law itself into question. So I'm not going to be able to complete this talk, so I'll skip around a little bit. I'm taking the third choice. I'm going to abandon the universality of the Newtonian paradigm and its fixed phase space. So it turns out there's a conservative way to abandon the universality of the Newtonian paradigm. Claim that only with the onset of life, with them, evolving biosphere creates new possibilities that expand the phase space that's no longer fixed. But prior to the onset of life, the Newtonian paradigm holds from the Big Bang onward in roughly the abiotic universe. So something special is happening when life happens. In this case, the problem of the past remains. The complexity of the current universe is e to the 10 to the 124th, and the initial state must pay the price. It's localized to the reciprocal of e to the 10 to the 124th. Penrose's dismay persists, but it doesn't get worse. So that's the move I'm going to take. I'm going to have to tune what I show you because we've only got a half an hour, but I want to now to show you that remarkable independent ground support exists to support the conservative way to abandon the universality of the Newtonian paradigm only at the onset of evolving life. So here we have our results up till now. Paul Davies in 2004, published a paper called Emergent Biological Principles and the Computational Properties of the Universe. Davies argues that any physical law must be implemented within the resources of the universe. Then he computes, given a maximum rate of elementary operations, 2e over pi, and the time from the Big Bang, and the estimated number of particles and operations, he concludes that an upper bound for the total number of bits of information that can have been processed by all the matter in the universe is 10 to the 120th. Now I'm quoting him, expressed informally, the existence of an emergent law in a system of sufficient complexity that its behavior could not be described or predicted by processing 10 to the 100 bits of information will not come into conflict with any causal closure at the micro level. Taking account of dark energy, Davis raises the distance to 10 to the 122. Davies concludes that proteins longer than about 60 to 90 amino acids and polynucleotides longer than about 200 nucleotides are open to emergent behavior, not determined by any causal closure at the micro level. Finally, Davies notes that many proteins in us are far longer than 90 amino acids, and many genes are far longer than 2,200 nucleotides. So this is the crux thing. Emergence is not ruled out. So I want to pause here. The whole thing is quite stunning to me. Here we have an estimate of the complexity of the abiotic universe, e to the 10 to the 120th, 24th, and a complexity of the biosphere, which is vastly larger than that. And Davies is saying you can't get more than on the order of 10 to the 120th operations. So let me go to the next slide. Davies' argument is entirely consistent with the complexity of the abiotic universe of e to the 10 to the 124th. It's just the exponentiation of 10 to the 122. Here, 100. So he's saying, what he's saying, I think, is consistent with saying the Newtonian paradigm holds for the abiotic universe, but not for evolving life. Taken together, the arguments of Davies and Cortes support the claim that the Newtonian principles for the abiotic universe. However, the vastly greater complexity for the evolving biosphere, e to the 10 to the 237th, now becomes strongly positive evidence for emergence with the onset of life. I just find this stunning. Maybe we can throw it out. And I only have 10 more minutes. So the huge excess of e to the 10 to the 237th versus e to the 10 to the 104th suggests that emergence in the evolving biosphere has been extremely important. So the remainder of this article suggests some reasons for this. I'm going to pause here. Assume this is true, then one of the things that now stuns me is, how did the biosphere get from e to the 10 to the 124th to e to the 10 to the 237th? Where did all the complexity out the window come from? You know, so we have very new questions. I will not be able to get through all of this, but let me sort of sketch this and take you far enough to make you puzzled. I'm quite obviously not a physicist, but I have lots of physicist friends. You guys are okay. I work on the origin of life a lot. So I want to ask you the following question. The universe is not ergodic above about 500 Daltons. So let me make the case. A typical protein in you has 300 amino acids. Consider a protein length 200 amino acids. How many are possible? There's 20 amino acids. So the number of possible proteins length 200 is 20 to the 200th power. That turns out to be about 10. What is it? It's some huge number. 20 to the 200th is 10 to the, I forgot. Anyway, it's some huge number. If you ask, can the universe have constructed all of them in the lifetime of the universe? The answer is no. The shortest time scale is the Planck time scale of 10 to the minus 43rd. There's about 10 to the 80th particles, and the universe is 10 to the 17 seconds old. It would take if all the particles ignoring space-like separation were making proteins length 200, it would take the current age of the universe times 10 to the 37th power to make all of those proteins once. So pause. It is true. As molecular complexity goes up, the universe is non-ergodic. It will not make all possible complex molecules in vastly longer than the lifetime of the universe. So the universe is not ergodic. It's not. That means that most complex things will not get to exist. So why are there human hearts? We all have human hearts. I've written about this a lot. You really have a heart. It's about 300 grams. It's an incredibly complicated thing in a universe that's not ergodic above about 500 Daltons. So how did the heart in you come to exist? So I'm going to ask my physicist to continue. How did it happen? How indeed have hearts come to exist in the non-ergodic universe? The basic answer is that life emerged and evolved. Hearts pump blood that sustains the life of the organisms with hearts. So organisms with hearts have offsprings that also have hearts. Therefore, those organisms whose hearts function better at sustaining the whole organism have more offspring. Natural selection, by selecting the organism, selects for improved hearts. Therefore, organisms with hearts evolve, and that's why hearts exist in the non-ergodic universe. Really take this in. The Newtonian paradigm and the whole tradition of physics since Newton is reductionism. We will explain everything from the bottom up. We will not succeed in explaining why there's hearts in the universe, only from the bottom up. This goes against Weinberg saying all the explanatory arrows point downward. They don't. Evolving organisms are selected at the level of the whole organism, and that's downward causation. It's not upward causation, and that's why the biosphere does things that are radically different. So I'm going to skip over all of this. I want to try, so this is a stunning thing, the stunning concept. This is a property that is newly seen, constraint closure, and it lives life, which is based on physics, above physics, in entirely unexpected ways. So here it is. What is work? Well, work is force acting through a distance. But Atkins points out that work is the constrained release of energy into a few degrees of freedom. So consider a cannon, a cannonball at the base of the cannon, and powder between the base of the cannon and the cannonball. The cannon is the constraint, and it's also the boundary condition. When the powder explodes, the cannon constrains the release of energy in the expanding gas to expand only along the bore of the cannon. Then the expanding gas does thermodynamic work on the cannonball, which is shot from the cannon. The critical thing is that without constraints on non-equilibrium processes, there can be no work. That's Atkins' point. Well, you guys, you sort of start with the boundary with a cannon. I asked a new question that will be obvious to all of you. Where do the constraints come from? At the Big Bang, there were no cannons. So where did the cannon come from? Well, it took work to make the cannon. So this is very strange. I'll call it the work constraint cycle. No constraints, no work. No work, often no constraints. Constraints can be constructed and can serve as boundary conditions. So where do the constraints come from? So this is a beautiful idea due to Monteville and Matteo in 2015. It's a transformative concept. So it's wonderful, it's just wonderful. I can brag about it because it's not mine. So here's constraint closure. In order to have work, you have to have some non-equilibrium processes to constrain them. Let's consider three non-equilibrium processes, 1, 2, and 3, and consider three constraints, A, B, and C. A constrains the release of energy in process 1 that does work construct B. B constrains the release of energy in process 2 that does work to construct C. C constrains the release of energy in process 3 that does work to construct A. Constraint closed systems do thermodynamic work to construct the very constraints on the release of energy into the few degrees of freedom that then constitutes the work that constructs the same constraints. Constraint closed systems literally do thermodynamic work to construct themselves. This is in a sense one of the deepest secrets of life. It's perfectly physical, but once you've got that, cells reproduce, which I can get into, and they do thermodynamic work to construct themselves. I've only got a couple more minutes. So here's an equation that I wrote down some years ago. It's a TAP equation, and it is the framework. I don't have time. So, but let me jump ahead. So this is so now I want to get to, hang on. So I want to try to find, I'm going to do this in about a minute and a half because I know we've got to be shut. How will we define the phase space for a non-ergodic system that never reaches its entire phase space? The basic idea, and I'm going to use this tap equation to do it, is to compute the total possibilities at some time t. A subset of those is actualized, calculate that, and then calculate the ratio, R, of the total possibilities divided by the actualized possibilities at any time t. So the ratio of the total possible to the actual possible is the current non-ergodicity of the system. The reciprocal, the actualized possible by the total possible, is the localization of the system. So that's now our candidate fourth law. And I've used this tap equation, and it has the following property. The total possible increases over time. The actualized possible increases over time, but the ratio of them, R, also increases over time. Namely, over time, what happens is the phase space expands and the actualized possible expands, but at a smaller rate. Therefore, the non-ergodicity of the system goes up, and reciprocally, the system, by doing work to expand its phase space, constructs itself in an ever tinier region of its ever expanding phase space. So I know that I got to be done, but so that's the fourth law. So the consequences are remarkable. It says that 1 over R, which is localization, can increase. And if that's true, entropy decreases, which I'll now show. So I'll go fast. But in a fixed phase space, no, we can come up with a request to what's the free energy cost per added degree of freedom. And roughly speaking, the free energy cost per added degree of them is roughly linear in the mass of things constructed. But the expansion of the phase space is exponential. So if I may have just a couple of extra minutes, I'll say it. Consider a biosphere with the longest peptide, its length n. The phase space is 20 to the n. That's all the possible proteins, length 20. Let a new peptide length n plus 1 arise. The new phase is 20 to the n plus 1. So the phase space is expanded exponentially, but it requires no more work and generates no more heat than required to generate a single longer peptide. The amazing implication is that adding the new degree of freedom becomes ever cheaper as the phase space grows. So so the fourth law says the cost of adding the next degree of freedom is less as degrees of freedom are added. I do not have time to do more than get here, but it's easy to test this with respect to the biosphere. We can say the biosphere, it's true, and the reason we know it's the following. What the fourth law says is it's ever cheaper to add the next degree of freedom. Therefore, with constant energy input, the system that can do so should construct itself into an ever smaller region of its ever expanding phase space. When life started 3 billion years ago, 3.7 billion years ago, the energy input from the sun is roughly constant for all of the existence of life. And current life has constructed itself into a very tiny corner of its phase space. There are proteins length 2000. So we are localized into a phase space. 20 to the 2000 is 10 to the 2600. And maybe 10 to the 60th things have been tried in the evolution of life. We're localized to an incredibly tiny region of our phase space. It's even more so if we consider that the biggest protein has 35,000 amino acids, each with 10 atoms. So there's a molecule in us that has 350,000 atoms. Consider the phase space of all possible molecules made of chin-ups, with 1 atom of chin-ups, 2 atoms of chin-ups, 10 atoms of chin-ups, 1,000 atoms of 350,000 atoms of chin-ups. That's the phase space of the biosphere, and we're in a tiny, tiny, tiny fraction of it. So to end, because it doesn't cost more to add the next degree of freedom, but the phase space goes up exponentially, the phase space is exploded at ever smaller cost. So entropy has decreased. If entropy is really decreased, it's stunning. And it also means that the second law can't be the global arrow of time. So that's the talk. And I did pretty well. I got it in. So that's an awful lot of stuff to take in. It's very foreign. And thank you.